Very first 5-minute quantum physics tutorial from quantumlifetime.com. My name is John Purcell, and in this series of 5-minute tutorials we're going to be looking at quantum mechanics. And quantum mechanics is one of the principal theories of modern physics, and what it is it's the study of the behaviour basically of very, very tiny things. Mechanics in this sense actually means the study of how something works. So we usually think of mechanics as being how an engine works, but in general the word mechanics is just the study of how any system works. And the system we're going to be looking at is the system of quanta, the singular of which is quantum, and a quantum is a very, very tiny, supposedly indivisible packet of energy. And in fact, since Einstein showed that energy and matter are interchangeable at some level, quantum mechanics can be thought of as the study of anything that's very small. Now, the reason that this particularly interests me is that there's kind of a problem here, a kind of philosophical problem, and also a kind of scientific problem, which is this. Quantum mechanics, we've said, applies to very small things, and it does work on the very small scale. When we're looking at subatomic particles and even entire molecules, quantum mechanics often seems to work, well, it seems to work extremely well. But when we look at large objects, for example a chair, let's say, or anything that we can observe with our eyes, or anything that we don't need an electron microscope to observe, quantum mechanics doesn't really seem to work at all. It doesn't seem to apply, because quantum mechanics seems to say that very small things don't have a state until they are observed. So we think of, for example, a chair as having a position whether we look at it or not. But in the world of quanta, when we observe things, we have to do an experiment that forces them to have, for example, a position. And when we're not looking at them, at least according to a standard interpretation of quantum mechanics, they don't have a position. So that things that are very tiny don't seem to have a position or any kind of state at all until we do an experiment that forces them to have some kind of state. And that doesn't seem to be the situation in the macroscopic world, the world of normal sized things. And various people have put forward various possible explanations as to why this should be so. And some people think that there's something wrong with the laws of quantum mechanics, although there doesn't really seem to be. They seem to apply very, very well at the small scale. Some people think that there's a boundary between the small and the large, and that below that size boundary quantum mechanics applies, and above it, it doesn't apply. And other people still argue that there's something wrong with our view of how things work. There's something wrong with our very view of actual existence itself. And I actually incline towards the latter view, and that's really why I want to delve into quantum mechanics mathematically in this series of tutorials. I think that quantum mechanics may well tell us something very deep about how our world actually works physically. Now, just to give you a little bit of the background of quantum mechanics before we finish this first tutorial. Quantum mechanics was derived in the first part of the 20th century, and in fact a lot of the main developments in it took place in the 1920s, and they were due more than anyone else to a guy called Werner Heisenberg, working around 1925. And quantum mechanics was then reformulated with an equivalent mathematical formulation by a guy called Erwin Schrödinger. And Werner Heisenberg's formulation we call matrix mechanics, and Heisenberg's Schrödinger's formulation we call wave mechanics. And although wave mechanics is more popular, I think it's Werner Heisenberg's formulation that's in some ways